A very good evening to all of you. It's actually a real privilege to come here and share with you the excitement of India's first interplanetary mission, the Mars Orbiter mission. And first of all, I take this opportunity to thank the organizers for giving me this opportunity to come and interact with the students. That I feel is really a great honor for me personally. As many of you would be aware, that this is in fact India's first foray into spaces beyond Earth's gravity. And the Mars Orbiter, which was launched on 5th of November 2013, after traveling for 300 days on its journey towards Mars, was finally injected into the Martian orbit on 24th of September this year. That is about a month and a half back. So my idea, the way I have made this presentation, is to actually tell you about not only the mission, but also the instruments that are on board this Mars Orbiter, so that you get an idea about what are the kind of scientific inquiries that we are planning. This is how the presentation goes. We start with that why Mars? Why did we send a spacecraft all the way to Mars? Then what were the mission challenges? Because this mission was not an ordinary mission. There were a lot of criticalities involved, which I'll try to bring out. I'll also be talking about the mission phases. What are the different mission phases that we had to go with throughout this I would say almost like 11 months. Then a little bit about the spacecraft and the rocket, as well as the imaging instruments on the Mars Orbiter mission, which are basically 5. The methane sensor for Mars, the thermal infrared imaging spectrometer, the Mars color camera, the Mars exospheric neutral composition analyzer, and the Lyman alpha photometer. As I said, actually, Mars is called a terrestrial planet. Terra means Earth. So it's quite a way, it's similar to Earth. You can see, but in many ways it's different as well. If you look at this table, then what it tells that the Martian atmosphere is made of 95% carbon dioxide, which is very different to what you have on Earth, where you have 78% of nitrogen. The pressure is nearly 1/100th of what you have on Earth. Similarly, you can see it's half the size. The distance from Sun is almost 1.5 times that of Earth. So that is very significant, and that I will try to bring out in some of the subsequent slides that I will be presenting. The gravity is nearly almost like 1/3 of that you have on Earth. So it means actually if you weigh 60 kg on Earth, if you go to Mars, you will be weighing nearly 24 kg. So that that's an instant weight loss program. So another thing is that similarity wise, the length of one day on Mars is also actually similar to what you have on Earth. It's almost 24 hours. But length of year is nearly more than twice of what that you have. It takes actually 687 Earth days for Mars to make one full revolution around Sun. The average temperature is minus 63 degrees centigrade as compared to 14. So Mars is much colder than Earth. That you can make out. The temperatures can vary from 133 Kelvin, that is almost like minus 140 degrees centigrade, to nearly plus 20 degrees centigrade. Whereas on Earth, you know actually that it varies from 245, that is minus 20 or minus 25 to plus 43. The tilt of axis is also there in the case of Mars, which is almost similar to what you have on Earth, and that is very important because it means you have seasons on Mars. Like you have seasons on Earth, you have seasons in Mars as well. And Mars also has a couple of satellites. We have only one moon. Mars has 2 moons, which are known as Phobos and Deimos. And another important fact is that Mars lies in the Goldilocks region. Now Goldilocks region is the part of the universe where they say which is neither too hot nor too cold, and there is a possibility of finding liquid water there, which is extremely important. So now the question comes that why Mars? I mean, why are we really interested in going all the way to Mars? One thing is that Mars happens to be our celestial neighbor, and we are always interested in our neighbors. Like पड़ोसी के घर में क्या चल रहा है, उसमें हमारी हमेशा दिलचस्पी होती है. So it's like that actually. So for Mars also we want to know that what really actually Mars is made of. What are the processes that are taking place? What Mars has to offer to us here on Earth. Mars has been an object of general curiosity as well as specific scientific inquiries since time immemorial. And the reasons are because Mars has many similarities, as I hinted in the last slide, with Earth. It has seasonal cycles, it has a thermal environment which is conducive to the evolution and development of life, and of course it has similar landforms. It means you have mountains and craters and peaks and valleys like you have on Earth. And another thing which is important here to tell you that why there is a recent, I would say that reignition of interest in the Martian exploration is because of recent detection of methane. And now methane is one gas which actually can have origin biotic as well as abiotic. If it has biotic origins, that is actually it is generated, or the origins lie in biogenic processes or the processes which are biological in nature, that may hint towards existence of life. So that is of course very important. If we can make a discovery that there is life on Mars, then it will be really a big thing. I thought that I will just present one small actually cartoon that I have taken from from the Facebook. There is a web page called which is being hosted by our organization called ISRO, is known as ISRO Mom page. So I have just taken one cartoon from there. It shows actually that Earth, you can see on the right corner, Earth is sending a probe towards Mars, and Mars is running all scared, helter-skelter, telling that no, yet another probe is coming towards me. Because it's trying to tell that we have sent so many probes to Mars, so one more probe is coming, which is our Mars Orbiter mission or the Mangalyaan, and Mars is running scared, telling that no, don't, yet one more probe coming towards me. I don't think I'm infected with life. So it's something I thought that I would just share with you people. And as I said, actually there have been many investigations carried out. People have sent their instruments, the satellite spacecraft to Mars, but still Mars remains an enigma. Still there are many puzzles to be solved. Still much needs to be known about Mars. I thought actually I would just present one small audio visual here, which will give a fair bit of preliminary idea about Mars.
The surface features like hills, highlands and plains, polar ice caps, its relatively benign surface temperatures, and its day, which is a little longer than an Earth day, has made humans gaze at it with curiosity and excitement. For centuries, humans have observed Mars as a red dot in the night sky, moving slowly against a background of fixed stars. Because of its red color, ancient Romans named the planet Mars after their god of war. People of ancient India named it Mangala, and the same name has remained in many Indian languages today. It is also known as son of Prithvi, Mother Earth. Systematic telescopic observation of Mars began in the early 17th century with Galileo Galilei's observation, which resulted in the discovery of many interesting things and optical illusions associated with the observations, giving rise to certain misconceptions. Prominent amongst them was the belief that Mars was the abode of intelligent life capable of building gigantic canals. This firm notion in the human psyche led to dozens of robotic spacecraft, including the Mariner 9, the Viking, and the Mars Express being sent to explore the planet after the dawn of the space age. However, not one of these robotic investigators has revealed the existence of even microorganisms on Mars, let alone intelligent creatures with superhuman capabilities. Nevertheless, Mars has not revealed all its secrets. Today, there are many fundamental and profound questions about Mars that are yet to be answered. Prominent among them are those related to the evolution of Mars and its suitability for the origin and sustenance of life in the past, or the viability of microscopic life today. Thus, there is a continuous and concerted effort across the globe to explore the planet by sending orbiter spacecraft to Mars, or putting landers and rovers on its surface.
Okay, so I guess I was able to present that, okay, some of the rationales behind sending the spacecraft to Mars all the way. Coming to the objectives of the mission, besides the scientific exploration, this particular mission is primarily technological in nature, and it's about designing, planning and executing an interplanetary mission with clear emphasis on deep space communication, because like I said, when you are going to Mars, you are actually traveling a large distance, almost like you are traveling over 650 million kilometers, and you are going to a planet which is on an average almost like 225 to 400 million kilometers away from you. So it's about communicating with the spacecraft all through the way, which is known as deep space communication, navigation and controlling the spacecraft. And also one important factor here is, like in one of the previous slides I showed, that Mars is almost like 1.5 times away from Sun as compared to Earth. So because of that, and because of the large distances involved between Earth and Mars as well, you cannot micromanage this particular mission. It means actually you can't send a command from here Earth and expect that it will get executed instantly, like you have for other missions or other spacecraft which are orbiting around Earth. Reason being, it takes approximately 12.5 minutes to almost like actually, I would say like 20 minutes to travel to Mars, and that much time again to come back. So you'll have to wait on an average for almost 20.5 minutes to 43 minutes to know that what has happened to a command. Suppose you want to say hello to your satellite, it would take nearly 12.5 minutes to reach there, and the satellite tells you that okay, I'm fine, and that will take another 12.5 minutes to reach you. So the total time that you would come to know that yes, the spacecraft is doing fine is nearly 25 minutes. So you cannot actually manage the mission from here. So a lot of smartness has been built into this particular spacecraft. It can take its own decisions. There are many decisions which can take on its own. So I will be subsequently actually touching upon these aspects as I proceed actually forward. So what this is known as onboard autonomy. So on the spacecraft itself, you have certain autonomous features built in. And as I said, actually the scientific objectives will be coming out, actually I will be able to bring out as I present these instruments. Now this particular mission has a lot of challenges. One of the challenges was about the radiation itself. If you have actually students here who would have read in their science classes that we have actually around Earth a certain radiation belt. Now this radiation belt is known as Van Allen belt, which basically consists of electron, protons and nuclei. This has very highly charged plasma particles, and this belt starts from almost like 1,000 kilometers from Earth's surface and extends up to almost 60,000 kilometers and is a part of the inner magnetosphere of Earth. Now these charged particles are extremely dangerous towards some of the components and the systems that we have on the spacecraft, and these can interfere with the functioning of these systems there, and not only that, they can actually badly damage them as well. So we had to actually take sufficient safeguard against these particles which are present in the Van Allen radiation belt, and the spacecraft during its course of its mission had to actually pass through this Van Allen radiation belt a number of times. The fact that spacecraft has been able to sustain that tells that actually that our design and the execution part of it in ensuring the safeguard measures have been adequate, and we have been able to take care of this particular threat, I would say. Then another factor, another challenge is in the case of thermal environment. You see, actually when we are around Earth, when the spacecraft is around Earth, it gets the thermal load from not only from Earth but also from Sun, and this is known as what is known as hot case. But as it starts moving towards Mars, because Mars is actually much further away from Sun, it actually starts entering into region where the temperatures are lower. Even the sun load is much lower that you would have in the vicinity of Earth. So that is what is known as cold case. And you would know that the mean solar load on Mars is only 42% of what you have on Earth. And worse, that because of the fact that the Martian orbit around Sun is highly elliptical compared to Earth. Whereas Earth moves in almost a circular orbit, Mars moves in an orbit which has certain eccentricity, and the distance varies It varies from 206 million kilometers from sun and goes almost up to 250 million kilometers. So because of that, what happens is the solar flux in the Martian orbit varies as well. And peak to valley, that variation is nearly almost as high as 38%. So because of that, the temperatures vary significantly around the Martian orbit. And all the subsystems had to be designed such that they take into account this particular factor. Another challenge was in terms of power. Again, actually this comes from the fact that distance of Mars is more from sun. So what happens is that what it takes to generate 1 watt in Earth orbit takes nearly 0.35, would be giving you only 0.35 watts in the Martian orbit. And because of that, what happens is that the solar cell operating temperatures which are there in the solar array, which is basically the main source of energy in the Martian orbit for the spacecraft actually. So it basically, the temperature varies from 2 degrees centigrade to minus 20 degrees centigrade. And so far as the power is concerned, as I said, it is mostly generated by the single winged solar array, giving you almost like 840 watts of power. And there are situations where this solar panel is not illuminated by sun, because the spacecraft enters into areas which are not sunlit. That time the power requirement will be supplemented by a lithium ion battery, 36 ampere hour, which will supplement under those kind of circumstances. Another thing is communication. That was a major challenge, and as I said, that you have to converse with the spacecraft, send signals, receive from it over a distance which corresponds to almost like 400 million kilometers. I mean, this is absolutely huge. For example, if you want to just compare the distance from moon from Earth is 4 lakh kilometers, that is only 0.4 million kilometers. But for Mars, it's almost like 225 million kilometers to 400 million kilometers. That is the kind of things that the distances that we are talking about. So the communication, at the heart of this communication system is there is actually a set of 3 antennas which are known as the low gain antenna, which will be catering to a distance of 1.4 million kilometers. You have the medium gain antenna, which would be actually catering to a distance of 400 million kilometers, and the high gain antenna, which does the job for throughout the mission, that is almost up to 400 million kilometers. And what you can see on this on the slide, on this the picture, is that huge disc kind of thing that you see, that is almost like 2.2 meter in diameter. That is the high gain antenna. Now coming to the phases of the mission. This particular mission, the Mars orbiter mission, had 3 phases. The first thing is the geocentric phase. Geo means Earth. So it is actually around Earth. That is the first phase. The second phase is when it comes out of it and starts its travel or its journey towards Mars, which is known as heliocentric phase. Helio means sun. So it is actually, in that case, it is moving around sun with the sun at its center. And the third one is what is known as the Martian phase. That is when it reaches the Mars and is captured by Mars gravity. And it is the third phase which is currently on. Now coming to the geocentric phase, you see actually that the spacecraft was launched into an elliptical orbit of nearly 250 kilometers, what is known as perigee, the closest point to Earth, and going as far as 23,000 kilometers, and progressively this distance from Earth, the farther distance from Earth was increased, which is known as apogee distance. You can see that starting from 23,500 kilometers, progressively it was taken to almost like 2 lakh kilometers, and every time that the spacecraft passed from its closest point, that is at the bottom of the right hand corner, you can see that the closest point, every time the spacecraft passed that point, and there is a liquid engine in the spacecraft which was fired, and the velocity of the spacecraft was increased. You know actually that if any object has to come out of Earth's gravity, it has to gain a velocity what is known as the escape velocity, which is nearly 11.2 kilometers per second. So the spacecraft had to acquire that velocity of more than 11.2 kilometers per second to come out of Earth's gravity and starts its journey towards Mars along that blue line that you can see on the extreme of this slide. And you see actually, why did we do like that actually? Why did we have so many orbits? Couldn't we go straight away? The reason is that the rocket that we had to actually, because that is the rocket we had. So we had to make use of the rocket. This is a small rocket. It doesn't really give you that much of force, so that actually, you know, like it can straight away go into the Martian plane, or the trajectory which will take the spacecraft to Mars. So we had to progressively increase the velocity of the spacecraft by going around Earth. And it's almost an analogous situation, I would say, that suppose you are climbing a mountain, suppose you have a very powerful lift, sit in the lift and you press a button and you straight away that lift takes you at the top of the mountain. But you can imagine that such situation doesn't exist, because that would call for an enormous actually very powerful motor. But suppose you are traveling on a car which the engine doesn't have that much of power, so what you would do is that you will take these kind of hairpin bends and this way actually climb to the top of the mountain. That is the analogy that I thought that I would present you. So that was the situation when actually this particular maneuver was adopted. And another thing I just want to mention here is that you see actually it is when the spacecraft had to be put into the trajectory towards Mars, it had to put in a plane what is called the Martian plane, and that makes an angle, the orientation is nearly 25 degrees, whereas 20 degrees was provided by the spacecraft maneuver. The remaining 5 degree was taken, what was actually managed from lunar gravity. The gravity of the moon was actually that factor was also accounted for. So basically I am just trying to point out that we took help or from whatever, even the celestial, from whatever celestial objects, the gravity of other planets, the gravity of moon was also made use of. So it was an optimum use of the resources that this particular mission tried to accomplish. Now coming to the heliocentric phase, you can see that actually the spacecraft, that pink circle that you can see is basically the orbit of Mars. The blue one is the orbit of Earth around Sun, and the green here dot that you are seeing is actually the spacecraft. So it came out of the Earth's orbit, of its orbit around Earth in almost a hyperbolic trajectory, and you can see that it proceeded. And this particular situation, this orbit was computed, was thought out, because this orbit is what is known as the minimum energy condition or the minimum energy opportunity, wherein you spend minimum fuel. That was also important, because our rocket that we were using didn't have the capacity to carry too much of fuel or too much of weight. So we took that factor into account, and this kind of situation occurs every 780 days. That is almost like over actually 2.5 months, 2.5 years I would say, that when Earth, Sun and Mars make an angle of nearly 44 degrees. So this is the condition, and that occurs on November 2013. Next situation will again come January 2016 and then again in May 2018. So had we missed that opportunity in November 2013, we had to wait till January 2016 or to May 2018. This is of course actually a different, different portions of the slide trying to show you that how the spacecraft actually progressed. You can see on the second slide on the top that green dot, it has almost reached the Martian orbit. Now that is zoomed, that is Mars, you can see over there. The spacecraft is coming. Actually the spacecraft overshot Mars when it reached the orbit, and then it was slowly, that velocity was decreased to be captured by Mars. And these things actually I will be talking about. You can see that the rocket on the spacecraft is firing. You can see over here that the rocket is firing, that is essentially to bring down the velocity of the spacecraft, so that is captured by the Martian here. So once it reaches Mars, the Martian phase starts, which is presently the phase, and the spacecraft was injected into an elliptical orbit with a minimum distance of nearly 400 kilometers and the maximum distance of nearly 80,000 kilometers. I will just, whatever I have spoken so far actually about the three phases, the geocentric phase, the heliocentric phase and the Martian phase, I will just summarize this. You can see that this is Sun, and this is Earth, and this is the orbit of Earth around Sun, and it had to gain actually velocity more than Earth's escape velocity. So that was completed, and then you can see there is Mars, the orbit of Mars around Sun, and this is where Earth was at the time of departure when the spacecraft came out of Earth's gravity, that is departed Earth, and there is Mars. You see now the Mars has started its journey, of course, because Mars moves around Earth, around Sun, and so does Earth, and this is how the spacecraft progressed. You see it is now taking its trajectory, now reaching close to Mars, and once it reaches Mars, there will be a certain maneuver done when it will be injected into the Martian orbit. Now this is a very important actually, this particular activity or this particular exercise, what is known as the Mars orbit insertion, was extremely crucial to the mission. This Mars orbit insertion, which was which is probably the most critical phase of this entire mission. So I will just try to explain that through an audio visual. This activity was
on September 24,
critical to the entire mission.
The Mars
So I will try to
orbiter
explain that
spacecraft,
in the
after
subsequent slides as well.
666 million kilometers, arrived at its destination in a hyperbolic trajectory. And from here, the orbiter will be inserted into the elliptical orbit of Mars. Mars orbit insertion is a very critical maneuver, which will be carried out with the combined visibility of 70 meters ground antennae located at Canberra and Goldstone, and the onboard medium gain antenna. It may be noted that Mars orbiter mission entered the sphere of influence of Mars on 22nd September 2014, and the final trajectory correction maneuver was carried out on the same day. Mars orbit insertion phase has demanded a large amount of preparation at spacecraft level. All the operations of Mars orbit insertion will be independently realized by the onboard processor by sequential execution of events without any ground intervention. The commands required for the same were loaded onto the satellite 9 to 10 days prior to this event, that is on September 14 and 15, 2014. Mars orbit insertion operation starts with changeover to medium gain antenna 3 hours prior to liquid engine burn start. This will be followed by forward maneuver 21 minutes prior to liquid engine burn, wherein the direction of satellite is changed and reoriented, pointing it to the desired thrust direction, so that the spacecraft velocity can be reduced by a desired amount. The spacecraft is held in the same configuration for some duration. Star sensors updates are enabled after forward maneuver. 5 minutes 13 seconds prior to burn start time, the satellite is eclipsed by Mars, and hence the solar panels are unable to generate power as the sunlight is obstructed by Mars and doesn't reach it. In this case, the onboard lithium-ion 36 ampere-hours batteries will provide the requisite power by the spacecraft. However, the spacecraft is still in the line of sight of Earth and will receive data from it. Thus, 5 minutes 13 seconds into eclipse, the actual burn start event will occur. The criticality of Mars orbit insertion burn lies in the fact that the orbiter should get captured without crashing into Mars or without leaving Mars. The liquid apogee motor is fired to slow down the orbiter's relative speed to the planet by 1,109 meters per second, and the velocity from 5.1 kilometers per second to 4.3 kilometers per second in relation to Mars. Getting anywhere between 200 kilometers and 11,000 kilometers will keep the orbiter in the Martian orbit. Nearly 4 minutes 20 seconds after the burn start, Mars occult starts. That is, the Mars orbiter will go behind the planet. As a result, no signal from the satellite will reach Earth for a considerable amount of time. Nearly 20 minutes past the burn start time, the orbiter is likely to come out of eclipse, and though the solar panels will start receiving the sunlight, it will continue to be operated on battery power. This is because the satellite is still not in the line of sight of Earth, and hence the switchover is not performed. The total duration of burn time is expected to be around 24 minutes. The satellite will come out from behind the Mars approximately 28 minutes after burn start. And that's when the occult will end and the satellite will once again be in the line of sight of Earth. The power generation from solar panel and telemetry will be resumed nearly 2.5 minutes after the end of occult, and data on Doppler measurement from the satellite is received, which will give the first information on the total burn performance. The reverse maneuver, wherein the satellite is once again reoriented, pointing the high gain antenna towards Earth, starts 1.5 minutes to nearly 23 minutes after the end of liquid engine burn. The reverse maneuver ends nearly 11 minutes after the end of burn, with the resumption of high gain antenna support. The Mars orbit insertion is completed. Thereafter, in the next 2 hours, the health parameters of the spacecraft will be verified, and the sequential operationalization of its 5 payloads will be carried out over a period of few days.
You would have noticed that in this audio visual, everything was told that it will reach, it will, but actually this is how it exactly happened. So obviously this video was prepared, the actual event took place. But this is actually, I'm happy to tell that this is how exactly it happened. But it didn't happen just like that actually. There was a lot of calculations, lot of simulation exercises that went into this. So, but before I go to those things actually, I thought actually once again, I would like to, for you, this is just a very small, very brief actually 30-second video, which is simulation video, which again tries to explain the whole thing. Just try to understand one thing, is that there are some critical elements in this entire exercise. One of them, that you have to reorient the spacecraft, what is known as the forward rotation. The forward rotation, why that was required is that you have to essentially, you have to align the spacecraft in such a way that the thrust that you give has to actually slow down the velocity. So the thrust direction had to match with the objective that you wanted to achieve, that is the bring down the velocity of the spacecraft. Now you had to bring down the velocity of the spacecraft. Why? Because when it approached near Mars, because of the gravity, because the gravitational pull of Mars, the velocity actually increased. So like in the case of Earth's escape velocity of 11.2 kilometers per second, Mars has an escape velocity of 4.7 kilometers per second. The spacecraft had a velocity of nearly 5.3 kilometers per second when it actually approached Mars. Now that had to be brought down to almost like 4.7 kilometers, less than 4.7 kilometers, to almost like 4.3 kilometers per second. So the velocity of the spacecraft was reduced by firing the rockets in the opposite direction precisely as at that point. Then you can see that, okay, this entire exercise was carried out. Okay, go to the subsequent slide. Is that, you know, like once the spacecraft was reoriented, the rocket was fired, the velocity was brought down. Actually the spacecraft entered into what is known as eclipse, that is started going behind Mars such that it was not receiving any sunlight. So that entire power generation had to be actually was depending on the batteries. So that was one critical activity. Then of course the engine firing took place. Then the spacecraft went behind Mars such that again Mars came between actually the spacecraft and Earth, what is known as occult, and that was, the duration was nearly 25 minutes. Subsequent to that, once it came out, then only the resumption of communication was established with Earth, and we knew that almost after a duration of almost, I would say like almost like 37 minutes, that whatever we have sent the commands from here, received back the commands, after 37 minutes we came to know that yes, we have been able to accomplish our job. So in the time wise, 24th September at around actually 7 o'clock in the morning, this entire exercise started, and as I said, it took actually almost like a 7:40 or 7:45. By that time actually only we came to know that this entire activity has been successfully, we have been able to do it. Now what were really the MOI, this Mars orbit insertion challenges? One was that actually we are trying to do something which was when the spacecraft was away from Earth, but also as far as 224 million kilometers. Then because of this the signal time, the time for the round trip, for the signal to go and come back was nearly 25 minutes. So for 25 minutes there was absolutely no idea what's going on. So you had to actually do nothing but send a command, wait for those commands to be executed, and hope patiently that everything goes well. Now, that's what actually is mentioned in the third point. Real-time detection and action was not possible, and that 82% of this total engine burn, which was nearly 24 minutes, the total duration, 82% of that took place when the spacecraft was actually behind Mars, and 80% of this total burn time, that is almost for 20 minutes, the spacecraft did not receive any solar energy. So that entire exercise was carried out through battery. And of course, another factor was that we are not able to actually take help of the low gain antenna because of the distances involved. So the criticality lied there, because low gain antenna has a like a very, very large field of view, almost omni, that is over plus minus 180 degrees, but that was not possible. So we had to actually, over a very limited FOV field of view, we had to communicate with the spacecraft. Now, one of the things which was extremely critical to this entire exercise, one of the subsystems was the propulsion system. This propulsion system, of course, has this liquid engine which we talked about, giving you a power of nearly 440 Newton. Then you have, this was assisted by 8 22 Newton thrusters, and you of course has the high gain antenna. And this entire thing, actually this propulsion system, you can see that it has 253 leak proof joints, and if in one of those joints, if there was even a micron of actually there was a hole or there leakage, then this entire exercise would have failed. So that had to be taken care of. It's through engineering and through the execution of the design, it was taken care of. Then you had many electrically operated valves and many actions which actually happened autonomously on the spacecraft. The spacecraft has certain intelligence built into it, and it carried out those commands at the exact time on its own without any ground intervention, because as I said, the ground intervention was not possible anyway. Now, elaborate actually calculations were done. We had this plan. You can see right at the bottom what you have, this red thing is basically, this is the liquid engine. So this had to fire exactly at that time and for a given certain duration. And you see that this is what is shown as the pressure and tank, wherein to actually fire the rocket you need fuel, but you need oxidizer as well, and there is certain mixing ratio of 1.65 between the fuel and the oxidizer, and this fuel and oxidizer had to be injected into the liquid apogee motor or the liquid engine through a certain pressure which was imparted by the helium. You see, actually you can see a yellow dot traveling all the way. It will be now be passing through the two oxidizer and the fuel, and now the rocket fires. So this is how actually the necessary thrust was generated, but that was plan A. Now suppose that didn't happen, there was some degradation in the rocket firing, or actually this event didn't take place, then we had what is known as plan B. In that case, what would happen, that the four small thrust rockets that you see here on this side, on that side as well, these are known as thrusters. So these 22 Newton thrusters would then have to be employed. And you see, now this whole process, the way actually the fuel and oxidizer flows through the pipelines, there was integrated pipelines with the plumb lines. You can see that what happens, that now actually are rerouted, so that instead of going to the liquid apogee motor, they now go to the thrusters, and the thrusters fire, giving you the requisite thrust. So this is what we had, actually the plan B also ready in case the first plan doesn't work. So that is the kind of planning which had to go into it. And there was a lot of criticalities involved, but primarily there were two factors, that suppose the liquid engine, there was some degradation in the thrust, it didn't fire, because you see what is to be kept in mind here, that this liquid engine was being fired almost after a gap of 300 days. So for 300 days the liquid engine was actually sleeping, so it had to be woken up. Suppose it didn't work to the extent that it was expected to work, then what would happen is that we would have entered into a different kind of trajectory, a different kind of orbit. So basically the idea of presenting this slide is that actually if this doesn't happen, then what happens? Then what were the options? So all these calculations were done actually very, very extensively and elaborately, and we were prepared for any eventuality. And not only the computations, nothing was left to chance. So we carried out certain simulation experiments also in our high altitude test facilities, and a large number of ground simulation tests were done, and it was ensured that we actually accomplished what we were supposed to accomplish. And it's no surprise that on 24th September 2014, MOM successfully entered Martian orbit. So I just wanted to convey to you that actually this each and every minute thing was thought about, was thought of very elaborately, and all the preparations were done. Now this entire exercise, how precise was all this? So there's an analogy, and this was not given by any ISRO engineer. It actually came from the one JPL, the head of the JPL Jet Propulsion Laboratory in NASA. And what he said is that if you go outside the Bangalore in a golf course and you hit a golf ball towards Los Angeles, then it has to enter into the hole, into the specific hole in a golf course which is there situated in Los Angeles when you are hitting it all the way from Bangalore. And what is interesting here is that the hole is not stationary, but it is moving. So that is the kind of precision, that is the kind of accuracy that you required. There was another analogy telling that actually if you have you throw a peanut, that you throw a mungfali ka dana, actually from a train which is just coming out of the station from Jammu Tawi, then it has to fall and it has to enter into the pocket of a captain who is actually running a ship all the way in Kanyakumari. So that is the kind of precision and accuracy that was involved. So these were just two analogies that I thought actually that I would just present to you. And if I talk in terms of actually that scientific numbers, then basically we had to arrive in a box of 50 kilometers. So we had to arrive in a box of 50 kilometers or a cube of 50 kilometers after traveling all the way over almost more than 650 million kilometers. And that would have called to a precision or an accuracy in terms of angle of 0.2 microradian, which is nearly 0.000001 degrees. So that is the kind of accuracy. If had we missed that, our mission, our spacecraft would have either crash landed onto Mars or it would have become a flyby mission. That is, it wouldn't have been captured by the Martian gravity, and it would have been a flyby. So we wouldn't have accomplished our objective. So basically, during this entire journey, the velocity of the spacecraft had to be maintained within 1 millimeter per second. 1 millimeter per second, mind you, actually where it had a heliocentric velocity, that is it had a velocity around Sun of almost 30 kilometers per second. And it is extremely critical in such operations to know the position and the velocity of the spacecraft. And the position of the spacecraft can be known as what is known as ranging, and the velocity is through the Doppler shift. I won't be going into the details of it because I guess actually I don't have that much of time, but if anybody has any question I can later answer. That how you know that the Doppler shift is actually a shift in the frequency when there is a relative velocity between the transmitter and the receiver. So all these factors were taken into account, but that is not sufficient. You see, actually, because the reason being is that ranging tells us what is the distance, but suppose I am measuring the distance between 2 points, but the 2 points are in an arc. So the distance between these 2 points, and once it moves in an arc, is same when it's moving around a circle. So even though the distance is same, actually the point has moved out. So that only the ranging and the Doppler shift wouldn't have been sufficient. You have to know the position angularly as well. So you have to precisely know a point in space in 3 dimensions, and for that we took help of what is known as differential one-way ranging. So besides the spacecraft being tracked by 2 ground antennas which are widely separated, actually a group of stars which is known as galactic nucleus, which is known as quasar, that quasar was as well tracked. Now quasar is fixed in the inertial frame, its position doesn't change, so its coordinates are well known. So that was also measured, and that was taken into account to get over any error that would account for, because the signals will be passing all the way from the spacecraft to the ground station through the troposphere and ionosphere of Earth. Now we also had to take into account the orbital perturbations. Now one of the key elements here is, so you see actually when you are sailing a boat on water, when you are actually in a river or an ocean, so the wind actually helps you in sailing, but at the same time the wind can be a disturbing factor also, because that can actually change the attitude, it can tilt the boat. Similarly, there is solar wind. When it's traveling on its journey from Earth to Mars, the spacecraft is being propelled by sun's gravity, but the solar radiation is also a nuisance actually, because what would happen, there is even the radiation of the Earth actually, like it disturbs, it provides a disturbance to the spacecraft in terms of what is known as the radiation pressure, and that would have actually varied the velocity or disturbed the velocity of the spacecraft by 1 millimeter per second per day. And because the travel duration was nearly 300 days, finally that would have been significant, and that would have actually put the entire mission in jeopardy, in danger. So that was also accounted for. Also the gravity of other celestial bodies, the moon, the asteroids and the other planets was also taken into account in our calculations, and that's how the trajectory was maintained, what known as the trajectory correction maneuvers. Initially we had planned actually for 5 trajectory correction maneuvers, but because of our calculations and maybe we were lucky as well that we had to actually resort to only 3 such trajectory correction maneuvers, and by skipping 2 trajectory correction maneuvers or the TCMs, we were able to save actually that very important fuel. Now before I move forward, I thought actually I would just present to you that this Mars orbital mission had certain firsts. It is actually the first mission in the world to successfully reach Mars in its first attempt. That is very important actually. Of course, the other countries, they started their ventures much earlier. So that time also the technological, the scientific knowledge wasn't that advanced. So we are in a position to take advantage of the failures of other countries. So we took those things also account, and it helped us. But the fact remains that we were the first in the world to actually reach Mars. In the first attempt itself, it is the first interplanetary mission from any Asian country which has reached Mars. China and Japan has also tried actually, but they have been unfortunate on this count. And of course, this is considered to be the most cost-effective mission, and the total expenditure was only 450 crores. That is comes to nearly 70 million US dollars, and if you compare that with that of Maven, it is nearly 670 million dollars. Of course, these are 2 different missions. It may not be correct to compare like that, but it is just to bring about the fact that it's an extremely cost-effective mission, and this entire mission was realized in a record time of less than 18 months. That was very, very critical, because as I said actually that we had to take help of this minimum energy condition where Sun, Earth and Mars at an angle of 44 degrees, because then only actually you will be able to spend minimum fuel in going all the way to Mars. And it means actually we had to launch by November 2013. So we had very less time. We had only 18 months within which we had to accomplish this entire mission, design it, conceptualize it, and execute it as well. And we had been able to do that. And of course, another factor is that we had one of the youngest ever team working on this ISRO missions, the Mars Orbiter mission team, with an average of team members of nearly 32 years. This is only of the technical staff that I'm talking about, the scientists and the engineers. Now coming to the spacecraft, this spacecraft of course had some heritage coming from the other previous IRS missions and the Chandrayaan-1 mission as well. But it had certain improvisations, because this was a different kind of mission. This was our first interplanetary mission. So there were certain modifications or improvements done in terms of the communication system, the power system and the propulsion system, which I talked about some time back. And of course, one of the key elements was the onboard autonomy. The spacecraft actually, this gives you the summary of the major spacecraft elements. I won't be going into details because some of these things I already talked about. Just take a look at the attitude and orbit control system, because this was extremely critical to this entire mission. You had this particular system had 2 star sensors. Now the star sensors actually look at stars in the inertial frame, and because the position of the stars are known, so you know with respect to those stars where is the spacecraft positioned. So that is the job of the star sensors. There are of course the solar panel sun sensor which look towards suns. You had the quartz analog sun sensors, and of course you had the actuators, which are small rockets in terms of the thrusters and of course the liquid engine, and the reaction wheels were there, so that you can actually maneuver the spacecraft to change its orientation as and when required. And it had 3 sets of antennas, which I already talked about. This is how the spacecraft, actually the primary structure of the spacecraft looks. It's basically a sandwiched panel of aluminum CFRP. And you can see that the spacecraft is basically cuboidal in its actually structure. There are 6 panels or 6 faces of like you have in the case of a cube. And you can see, you can see the intricate actually those small, very narrow lines and like pipelines, which are basically a part of this propulsion system. Now you can see that the titanium tank, which is basically the fuel tank, that is being integrated onto the spacecraft. This is the integration of the liquid engine right at the bottom of the spacecraft. You can see that which I already showed in the simulation. So that's how that's the liquid engine, which was extremely critical to this entire mission, which I tried to point out in my earlier slides. This is the integration of the panels. These panels actually are on which the subsystems are put, including the instruments, and these panels are then integrated onto the primary structure of the spacecraft. This is a sneak peek into the inside of the spacecraft, and the black that cylinder that you see is basically the helium tank, which basically 67 liters of helium was put into it, which gave the necessary pressure for the requisite flow of the fuel and the oxidizer into the liquid engine. This is the spacecraft undergoing the EMI-EMC test, which is electromagnetic interference and the electromagnetic coupling test, to ensure that there is no electrical disturbances actually throughout its development and also its journey towards Mars. Then you have the testing in what is known as assemble mode. That is, the instruments have been integrated onto the spacecraft and they are now being subjected to certain tests. And this is what is known as the thermal balance test, wherein actually this is how basically it tells that this is how the sun shines on the spacecraft when it's traveling in its path towards Mars. So this is already simulated and the tests are carried out to ensure that there are no surprises during its journey. And this is the illumination check, wherein the solar cells in the solar panels are illuminated and their performance is checked to ensure that the solar cells or the solar panel will function as per the design throughout the mission life. This is loading the spacecraft in the thermovacuum chamber. It's a very large chamber, which is known as the large space simulation test chamber. When the spacecraft is being lowered into it, where the spacecraft will be tested, was tested for different temperatures under vacuum conditions. Because in space you don't have any air, you have vacuum. So you have actually pressures go down to level of almost like less than 10 to the power minus 6 torrs or 10 to the power minus 8 torrs. That is the kind of vacuum that we are talking about. So the spacecraft is tested for those under those conditions. And this is the spacecraft now finally fully decked up. That yellow draping that you can see around the spacecraft is basically what is known as the MLI, the multi-layer insulation blankets, which basically protect. This is like the blankets that you put on in winters, which preserves your body heat and doesn't allow the heat cold air from outside to come and actually disturb you. So like that, the spacecraft is also covered under blanket, which is known as the multi-layer insulation blanket. So you can see now it's now ready. The spacecraft then was shipped to SHAR by road actually. Now SHAR is the Sriharikota, which is basically ISRO's spaceport from where the spacecraft was launched. It was once in the spacecraft, it was taken out. Now this entire decontamination portion is also something which is extremely special. It is not an ordinary container. I won't be going into the criticalities of it, but anybody who has question, I will be happy to answer. So once it was taken out of the container, certain measurements were carried out. The moment of inertia, the center of gravity, etc., which are known as physical parameters, they were measured. Then again another look of the spacecraft being tested at Sriharikota. Then the propellant filling into the spacecraft is going on. The fuel and the oxidizer are being loaded onto the spacecraft. And this is how the spacecraft looks when it was integrated onto the 4th stage of the PSLV rocket. And what you can see is the two panels that you can see on either side of the spacecraft are basically known as the heat shields. Once they close, the heat shield protects the spacecraft. When it takes off from Earth, actually almost a distance of almost like 100 kilometers, you have this presence of air, and the air molecules actually, because of the enormous velocity of the spacecraft or the rocket, the heat that is generated is also enormous. It's very large amount of heat, and the spacecraft has to be protected against that. So that is being accomplished, or that is actually ensured by the heat shields. So this is how finally the spacecraft looks when it is actually covered by the rocket, and it is now ready for the final checks. You can see the coming to the rocket. It's the PSLV rocket. It's of course modified, and it is incidentally the 25th flight of the PSLV rocket. Again, this rocket, the height was almost like 44 meters. That is almost like, I would say, the 10 to 12 story building. That is the height of this PSLV rocket. And this shows the first stage of the rocket. The first stage basically comprises of 5 different modules which are integrated one after another. And you can see in the central slide, the central portion of the slide, that the different portions are being integrated with on each other. And then you have the strap-on motors which are integrated after the integration of the first stage is over. This is the integration of the second stage onto the first stage. And then the third and the fourth stages are then integrated. So you see actually one by one all the 4 stages are integrated onto the rocket. And then this is how it looked just before the launch on 5th of November 2013. So this the spacecraft, the rocket, the ground systems are now all ready for the launch. This photograph was taken just the night before the launch took place. And then the countdown begins. You would have, if you have seen the launches earlier, you would have known that the countdown actually goes in the reverse here. So you start from like 400, 399, 398, like that it goes on. And then finally the ignition takes place exactly when you count down for 10, 9, 8, like that, when it goes to 0. Precisely at that point the ignition takes place. And the ignition, then the rocket was ignited, and the liftoff, the rocket zoomed into space, and it was actually truly up and away on its onward journey towards Mars. They are on their onward journey to space, right? But the spacecraft has to be commanded, the rocket has to be commanded, controlled from Earth, and that is what is accomplished by the ground segment. And one of the very important elements of this ground segment is the 32-meter antenna, which is at the outside, at a place called Bailalu, which is at the outskirts of Bangalore. And this 32-meter antenna, I just wanted to tell you that how big is it actually. You may not be able to, the scale of a person, this is just to show you the kind of scale that we are looking at, because this is the antenna which sends the signal to the spacecraft, which is away from you, almost like 225 million kilometers, and again receives back that signal from space, from an object which is that far. So this antenna has to be actually 32 meters. You of course have 70 meters antennas also as well in JPL NASA. And this particular this is basically the hub of this entire mission activity. This is known as the Mission Operation Complex. This is again in Bangalore, in one of our units, which is known as ISTRAC, ISRO Telemetry and Tracking and Commanding. And this shows the network of the ground stations. These are basically the major milestones. The Mars orbit insertion took place on 24th of September, so fine. Now coming to the imaging instruments on Mars orbiter. Now this Mars orbiter is carrying 5 instruments, as I said, and this particular slide tells you that what are those instruments. This is actually the Space Application Center in Ahmedabad, from where I belong, actually has given 3 instruments: the Mars color camera, the methane sensor for Mars, which will look for methane. Then you have thermal infrared imaging spectrometer, which will measure the surface of the temperature, the surface temperature of Mars. Then you have one instrument called Lyman alpha photometer, and this Mars exospheric neutral composition analyzer, coming from Bangalore and Trivandrum respectively. Now this slide actually tells you about the payloads of the instruments at a glance. The methane sensor for Mars will try to measure the presence of methane in the Martian atmosphere to a very, very high accuracy. And as I said, actually in my first or second slide, I told that methane is extremely important, because if there is any methane detected in the Martian atmosphere, that would hint towards the existence of life. That would hint towards that may or may not be, life may or may not be. But still, if there is some methane, there is a possibility of life. Then thermal infrared imaging spectrometer, that will be measuring the temperature, and also it will be giving the data about the minerals that are present on the Martian surface. The Mars color camera will be sending the visuals of the, and many of you would have seen actually the images that it has already beamed back to Earth. Then you have the Mars exospheric neutral composition analyzer, which is going to measure the neutral composition of the Martian atmosphere. That is, what are the species or what are the gases which are actually there in the Martian atmosphere, what are the ions, what are the which are present in the Martian atmosphere. The Lyman alpha photometer, which will be trying to investigate, because we know that that Mars was once upon a time it was a wet planet. There are evidences that there was liquid water once upon a time actually probably flowed on the surface of Mars. So where did all that water disappear? So that fifth payload, Lyman alpha photometer, will try to investigate that what were the loss processes, loss of water from the Mars, from Mars. Okay, this slide actually I would just like to tell you. But the entire critical factor was that our time, we had only 18 months, and each of these five payloads we had to develop 3 models, which were the verification model, the qualification model, and the flight model, and that called for almost building actually 15 instruments in 18 months time. So actually that was extremely critical. We took help of certain improvisations were done in the design and the development of these instruments. And the orbit of this MOM is also a very special orbit. It's a highly elliptical orbit, so it gives us a lot of opportunities for us to carry out certain observations which will be extremely important so far as the space research is concerned. So I would be that this was also taken into account while designing the instrument. And this is the methane sensor for Mars. This is how it looked like. One thing I would just like to point out, that we had only 15 kgs of weight allocation, the weight budget that was available to us, and we had to make 5 instruments within that 15 kg only. So that was another factor which was extremely important. The power also was at a premium, so that was also taken into account. These are the principles of MSM. It is based on the Fabry-Perot-Etalon. I guess actually these are specific scientific things. Actually, maybe if somebody is interested, I can discuss further in details. But as of now, I will just skip this. Then these are some of the subsystems of the methane sensor for Mars. This is how the instrument was realized. You can see that how it was built up. Then this is a test and evaluation which was carried out. This is coming to the next instrument, the thermal infrared imaging spectrometer, the different subsystems. The Mars color camera, which is like a digital camera that we have, but of course it is much more advanced than that. It has many features which you don't have in your typical digital color cameras. These are some of the MCC images which were taken as a part of testing, on ground testing. And this is the MCC view Sun and Moon that was taken of not from Mars but taken from Earth, of course, as a part of our testing, ground testing. And this Meinka instrument, which I told, actually I won't be going into the details again. The Lyman alpha photometer, which will be as basically the 2 cells, the hydrogen and the deuterium cell. So it will basically be measuring the deuterium to hydrogen ratio to find out the loss processes of water. This is how the spacecraft, the instruments were located on the spacecraft. The spacecraft onboard instrument, the onboard performance of the instruments were tested throughout this course of this mission, and I'm happy to tell you that all the health parameters are normal and all the instruments are working fine. This is the first image taken by the MCC, the Mars color camera, during its Earth journey, and this is the first image acquired by the Mars color camera. This was acquired on 24th of September, when this now region on Mars, which is known as Elysium. I just want to show you that one of the moons of Mars was captured by our camera. You can see that this is how actually it was in motion, and it was captured by our camera. This is known as Phobos, one of the satellites of Mars. This is the another satellite of Mars called Deimos. This image was acquired on 14th of October. So I would just now I'm concluding my presentation, telling you that the journey is on. We have reached Mars, but the spacecraft is orbiting around Mars, and of course journey is definitely on. So stay tuned. I request all of you to log on to the ISRO MOM Facebook page, and you will get all the updates. And I would just share with you some of the images that were there. Actually, this is a spontaneous exhibition, spontaneous demonstration of the the happiness or the excitement that was there in these are the ordinary people actually, like out on the streets celebrating once Mars, our orbiter, entered into the Martian orbit. And this is an image actually showing the school children, and they are just telling that, okay, this is marvelous. So this is actually how, and that's all I wanted to present. Thank you so much. Thanks for your patience.